When a force is applied repeatedly at the natural frequency of any system, large amplitude oscillations result. This is the phenomenon of resonance.
Have you ever seen a singer break a wine glass with his voice? Well, I'm going to do that for you today. But before I do, I have to tell you that it's very difficult, even if you have a magnificent voice like mine. For one thing, you need a very special wine glass. It has to be thin and delicate so that it's not impossible to break, and it has to have a very pure tone. In other words, if you tap it, it has to go ping and not thunk. Well, if you know anything at all about wine glasses, you'll know that that can be summed up in just 2 words: very expensive. So I went to the physics department and I said, I need you to buy me a very expensive wine glass. And they said, Goodstein, why don't you drink out of a paper cup like everybody else? So I said, no, it's for a demonstration. And they said, all right, we'll do the usual thing. And they did. They appointed a committee. So the committee met and deliberated and thought about it, and finally they decided that they would appropriate enough money to buy me one very expensive wine glass to break for you. And here it is. But before I do it, I want to explain to you why it's going to happen. It has to do with a phenomenon called resonance.
On the 1st of July, 1940, a delegation of citizens met in Washington State. The weather was beautiful, the occasion historic, and the speech-making and fanfare altogether appropriate. This was the grand opening of the Tacoma Narrows Bridge. From the beginning, the bridge, which spanned Puget Sound between Seattle and Tacoma, was traveled in style, as well it should have been. The Tacoma Narrows Bridge was one of the longer suspension bridges on Earth. And if somebody hadn't overlooked something, it probably would have remained one of the longer suspension bridges on Earth. The problem wasn't that right from the beginning, a lot of people didn't pay a lot of attention to details. They did. But somewhere along the line, and this was obvious in the end, it looks as if someone forgot the significance of resonance. Resonance. Just as its sound lingers in the air, the word itself remains in the language. Resonance, from a Latin noun meaning an echo. But resonance conjures up more than linguistic echoes. In battle, for example, one hears of the resounding victory. But setting connotations aside, resonance can be seen as a simple mechanical principle of the physical world. Pleasant sounds are usually pleasant precisely because of the way they resonate. Of course, artistry is a factor, so are composition, setting, and mood. But resonance is essential. With a violin or a cello, the strings' vibrations at hundreds to thousands of cycles per second cause the whole instrument to vibrate at the same frequency. Every vibration gives the instrument's sound box a tiny push, so that the sound box vibrates resonantly. In turn, those vibrations excite resonant vibrations of the air inside the sound box. The quality of a fine instrument lies precisely in its ability to resonate equally with every note that's played. When a vibrating system is pushed or driven, at the natural frequency of that system, resonance occurs. Inside a piano, vibrating strings make the soundboard resonate. This resonance is being driven by the natural frequency of the string, which is about 256 pushes per second at middle C. Each time the string is struck, it makes thousands of oscillations, each one adding to the resonant response of the soundboard. Repeatedly pushing an oscillating system, with even a small force each time, makes successive oscillations grow bigger and bigger. The results are vibrations of increased amplitude. Even if these pushes are quite small, resonance will result. This vibrating tuning fork sets the surrounding air molecules into harmonic motion. Because air works as an elastic medium, it's a good conductor of traveling oscillations or waves. Each oscillation gently and rhythmically pushes against the air, sending out waves at the natural frequency of the tuning fork. When the pitch of the note struck on the piano is the same as that of the tuning fork, even if the fork isn't actually struck, waves from the piano can disturb it and set it into motion by means of resonance. The tuning fork and the piano string are examples of naturally oscillating systems. And though they appear more complicated, they obey the same basic differential equation as the simple mass on a spring. Like a mass on a spring, they have an internal force, F, that naturally opposes any disturbance, X. That means a differential equation whose solution is a sine function representing oscillations at a natural frequency, omega naught, that depends on the characteristics of the system, which are in this case, K, the stiffness of the spring, and M, the mass of the bobbing object. This is another oscillating system with a natural frequency. In fact, the child and the swing are a kind of pendulum. The frequency may be 1,000 times lower than the frequency of audible sound, but the principle's the same. A slightly larger mass, this one with longer legs, has learned to provide her own periodic push by shifting her body weight, kicking forward as far as possible, and tucking her legs under. Correctly applied at the same point on each cycle, that is, in phase, this young swinger displays her mastery of the phenomenon of resonance. But a true mastery of the phenomenon is best achieved by starting with an oscillating force that doesn't produce resonance.
Whether a swing or a spring, oscillators have their natural ups and downs, produced by the internal force, F. If an additional force, proportional to F naught, is applied at a different frequency omega, the result is a more complicated motion. And a more complicated differential equation. But the motion is really just two simple motions added together. Which solve the differential equation leaving an equation for A, which is the size of the new oscillations produced by the additional force. The size of these oscillations depends on how big the force is, A naught, and on how close its frequency, omega, is to the natural frequency, omega naught.
Here are some key elements of resonance: a forceful voice, exquisite control of frequency,
the amplified voice of Ella Fitzgerald shatter this glass?
and an oscillating system.
Whether it's a wine glass or a spring, the amplitude of forced oscillations is sensitive to the frequency. A force at low frequency, omega, driving an oscillator of natural frequency, omega naught, causes complicated but tiny vibrations. At higher frequency, the vibrations get a little bigger. But if omega gets close to omega naught, then even if the size of the force is very small, some pretty spectacular things can start to happen. Added to the natural motion, a low-frequency force has its effect. At higher frequency, the effect can be more interesting. But if omega gets close to omega naught, the effect can be positively shattering.
Can the amplified voice of Ella Fitzgerald shatter this glass? Believe it.
Only a tiny oscillating force is applied to this glass, even though the power behind it is Ella Fitzgerald's magnificent voice.
Now we ask, is it live?
But it takes an equation to show precisely why a singer with power and control can have such a shattering impact. Of course, the differential equation does leave out a few interesting details. One of the more interesting is that glass itself is a viscous fluid. A very, very viscous fluid. In fact, glass is so viscous, it takes centuries to flow. To flow downward through time and space, where it settles along the eventually thicker bottom of the pane. Glass is so viscous that it seems solid indeed, and even rings and resonates. Of course, it's the viscosity of the glass that prevents its resonant oscillations from becoming infinite. And without that viscosity, there wouldn't be an unbroken piece of glass left in either the old world or the new, where the effects of resonance can be seen and heard just as well. For example, while music is generally a pleasing example of resonance, the same can't always be said for the common rhythms of contemporary society. As an annoying example of resonance, consider the vibrating window. At the same time, however, while the panes may shake, rattle, and roll the listener to distraction, Built-in friction and viscosity usually keep them from shattering. Sometimes, as studied inside the Caltech seismic laboratories in Pasadena, the effects of resonance are more than annoying. They can be devastating, because they can amplify what is already an elemental, almost irresistible force of nature. During an earthquake, seismic waves are sent out from the epicenter in a range of frequencies. Compared to audible sound, these frequencies are generally very low. At earthquake frequencies, buildings between 5 and 40 stories tall are typically resonant. When these model buildings are shaken at a given frequency in a simulated earthquake, one or another is set into resonant vibration, depending on the frequency. Generally speaking, a complicated structure like a building will shake or twist resonantly at a number of natural frequencies. Engineers can minimize resonant responses by designing isolation and energy absorption into the building. And with strict adherence to earthquake ordinances, a structure has a way to resist being ripped apart at its very foundations. Building codes are laws. And when people think some laws are made to be broken, some buildings are bound to suffer the consequences. These sounds, produced by the wind acting on the wire, are another effect of resonance. These wires sing their song by vibrating at their natural frequency, because, to make some rather simple music, the airflow around a taut wire creates some rather complex patterns. Perhaps telephone wires only really sing in mystery stories, in fiction, where their eerie lyric harmonizes with the howling wind. But should telephone wires ever sing in fact, their song will be a composition of the phenomenon of resonance and the ever-present wind. In high winds, the normally stable airflow around a cylinder, this wire for example, becomes unstable. As the wind tries to close up the gap on the downwind side of the wire, to prevent a vacuum, eddies start to form. Soon, the eddies start peeling off and running in the downstream wake, creating a predictable flow pattern. Every time a vortex peels off, it gives the wire a little push. At a certain wind speed, the vortices start peeling off at a resonant frequency of the wire, setting it into motion. This effect is called an Aeolian harp. The skill it would take to tune these strings was handed down from the Aeolians, the ancient Greek tribes which settled on and around the coast of Asia Minor. But the skill it takes to play the Aeolian harp comes from the magic fingers of the wind. When air blows across the strings, the principle of the Aeolian harp, the phenomenon called resonance, explains the dramatic song of wires in the wind. Perhaps, among other things, the Tacoma Narrows Bridge was the most spectacular Aeolian harp in history. Unfortunately, its first performance was destined to run only about 4 months. In the meantime, she was a beautiful bridge. Beautiful, but a little strange. Even before construction was completed, people observed its peculiar behavior. That was because, even in a light breeze, ripples ran along the bridge. After a while, one of the local humorists called her Galloping Gertie. And for fairly obvious reasons, the name stuck, at least until the 7th of November, 1940. Then as now, Seattle and Tacoma were sports-minded cities. For 4 months, a regional sport was to drive across the bridge on a windy day. While some claimed it was like riding a roller coaster, others found it a little disconcerting to see the car in front disappear. How popular this bridge sport was, or to what extent it might have spread across the country, is anybody's guess. On November 7th, 1940, the winds were relatively moderate, about 40 miles per hour. A new mode appeared. Rather than ripple, the bridge began to twist. A wind of 40 miles per hour is not too strong, but it was strong enough to start the bridge twisting violently. And at 11 a.m., it fell. Investigators were mystified. A bridge constructed according to the best engineering standards of the day, perhaps the best bridge in the world. This was not a bridge that was supposed to collapse. What in the world had happened? Theodore von Karman, a Caltech professor and a pioneer in modern aerodynamics, came forth with the answer. Von Karman's explanation of vortex shedding and resonant oscillations was not universally popular among construction engineers. However, as verified by wind tunnel tests at Caltech and at the University of Washington, von Karman's explanation was correct. And ever since, no major bridge is completed without first passing the test of the wind tunnel.
All right? The time has come to break the wine glass. But I'm not going to do it with my own voice. My contract with the Met won't permit that. And there's another problem. This takes practice, and I only have the one wine glass. So I'm going to try it first using this ordinary laboratory beaker. Now here's how it's going to work. All of this stuff here is going to substitute for me and make a pure tone. That'll make the beaker vibrate. And then I've got this microphone here which is listening to what the beaker does. And the output of the microphone is on this oscilloscope, so you'll be able to see on the oscilloscope what the beaker is doing. Watch this. You see that? Okay. Now, what I have to do is to turn up the volume, and that makes the beaker vibrate. Now you can see that the beaker is vibrating, but not very much because it's not exactly at the right frequency. It has to be at precisely the right frequency, the resonant frequency of the beaker, in order to vibrate enough to make it break. So I'm going to tune this to the right frequency. There it is, right there. That's it. All right? Now all I have to do is to turn up the volume all the way up, and it'll break the beaker. Okay, you ready for this? Now the people in the first couple of rows, your ears will bleed a little bit, but don't worry about it. It's not serious. You ready for this? Here we go. So we managed to do it without ever breaking this exquisite wine glass. You see, that's why they bought it for me. They knew I'd never get around to breaking it. All right? That's it for today.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.